A czy coś słychać? Czy słychać? Great. Thank you very much. Sorry for the delay because of technical difficulties which probably were related to VPN, but also other stuff. We'll try to continue with the lecture with just a slight of 35-minute delay. Last time we finished on the discussion of generally linear models. We've discussed different types of likelihood. There were multiple ways of creating models depending on what kind of data are we considering. And this time we want to focus on linear models, because when I finished last time, I think that I've put a little too brief introduction to the topic, and today I wanted to look somewhere in depth to consider a model that can be interpreted as something, and perhaps to try to construct something that we'll be able to discuss model comparison methods, we'll be able to discuss some other stuff. So let's begin. As we discussed previously, one of the models to represent the data that we collected is to create a model that will try to incorporate character of data, so for example real numbers, certain uncertainty of data collection, data generating process, in case of standard deviation, and some kind of underlying process that's happening here, which is the mean of the normal distribution. However, the mean has is a functional relationship representing some kind of predictors. So our outcomes, our observed outputs, are being generated by a process and observed with certain uncertainty. And creating a model with Bayesian framework relies on it that we assume that outcomes are normally distributed, each outcome has its own mean, and this mean is dependent on the predictors, and this dependence is a linear, in this case, a linear relationship where for each of the parameters we've assigned certain prior distributions representing some information. And case when there is a single sigma, single standard deviation connected with all the measurements, it is called a homoscedastic model. That is, the uncertainty in this case is homogeneous among all the measurements. On the other hand, there is also an option that for each measurement, or for some groups of measurements, there will be different sigma, different uncertainties. Such case is a heteroscedastic model, which really, in case of Bayesian frameworks, doesn't differ that much, However, it might be much harder to fit, to represent the data. However, this is always possible to construct this way. So, this is a typical formulation of such model, and we'll try to discuss how we can arise in such model, how we can complicate it, how we can work on it. And we work on linear models because, as I mentioned before, this is something that all the automatic control is based on, a lot of things are based on, that practically all nonlinear relationships can be locally approximated by linear functions. The most important aspect is how locally, because as long as function is at least once differentiable and this derivative is not zero, the linear representation is at least viable in certain neighborhood of the point we are linearizing it. This representation is generally available through all the world and through over the science. However, it has certain limitations. First of all, this locality might lose sense rather quickly. The always recurring history of the bumblebee, which according to laws of physics cannot fly, but is too stupid to know it and flies, is of course the situation of bad modeling. In that case, the sine function was being represented by its linear approximation, that is the x function. Sine of x is locally similar to x. So that representation created a model that neglected the higher terms, neglected the stronger nonlinearity. And if you don't neglect that, all the laws of aerodynamics work and bumblebees can fly as they really do. The problem is also in case of social sciences or biological sciences. If someone is too trigger happy with their model, they can forget that this relationship is only local, and they want to use linear representation through all spreads of parameters, which might make sense or might not. Depends on how large uncertainty we have, because sometimes uncertainty is such large that if it's quadratic or it's polynomial or it's linear, it doesn't make sense if we are completely uncertain what the actual measurements are. So the general idea that we can collect with linear models is this so-called idea of geocentric models, because using the Ptolemaic model of solar system, where Earth was the center of the universe, it was obvious that the orbits of planets and sun does not work. They were just not working to represent the relationship between planet and Earth. So, unfortunately, instead of revising the idea that Earth is the center of the universe, they wanted to find a mathematics that would explain that. For this purpose, it created so-called epicycles. And the idea of epicycles was that planets were not actually orbiting the Earth, but on circles. They were, on each circles, there were like a center of gravity of a given planet was following a circle on the Earth, and the planet by itself turned around this center. So we had two oscillating moves all together. And if two was not enough, we could add third. And this, of course, was completely wrong. It doesn't work this way. That we cannot represent the planets do not move this way, right? Oh, I've noticed that I haven't shown you myself, and probably I won't, because I'm not sure how to. Oh, I can. Okay, I'm here. So generally, planets do not move this way. They do not move on the epicycles, but the computations were working. Adding epicycles into our model allowed representing the movement of planets consistent with observations. And why is that? It happens because actually representing this movement as an epicycles is nothing else than representation of such a movement as a Fourier series. Adding additional terms in Fourier series is equivalent to adding additional epicycles, so the approximation of the function is better and better with more epicycles. But of course, this is not an actual causal relationship. And that is generally the point of statistical models and machine learning models and many other models, is that they are not necessarily causally right, but they can be accurate. And models can provide us with good predictions, but do not provide us with good understanding of the phenomena that happens. If we do not have the understanding of that phenomena coming from some kind of expert knowledge, then statistical model that gives us quantitative information is still rather a good thing, but we need to understand that certain relationships are just not causal. They are correlations, and certain things can predict things very well. For example, there's a famous case of racial discrimination history where there was a medical school that was using auto-grading of essays applying students to catch them in the not catch them, but just to recruit them to the schools. And they've decided, of course, in order to create the system to be completely transparent and free of prejudice, they removed such aspects as race or gender from the surveys. So when the data were being evaluated, it did not take such information into consideration. However, what they did not find, that certain elements of survey were still very good predictors of racial background or economical background. For example, certain aspects regarding the style of the application letters, like numbers of typos, numbers of words being used, vocabulary being used, stuff like that, which could be graded by a person but then put it into an algorithm, were very good predictors of racial background, because especially in the United States, people from the African American backgrounds usually had in that time problems with getting to better schools and so they received marks in that aspect much lower than the others. So the model that used the grading of an application letter was a very good prediction of race. But we can actually, without any doubt, say that there is not any causal relationship between how people write their essays and what race they are. There is no relationship here. There is a relationship with on the opposite side, and also not direct, but rather based on the economical background, social background, etc. So those things were good predictors, no causal relationships. But still, this is a good point of when using linear models or other simple models, they can be good predictors. But not necessarily they can allow you to make good, sensible representation. And we will now, so what we discuss here are linear models, but what is being called in literature is regression, preferably linear regression. And this is a problematic word that generally what was called regression to the mean was, for example, situation where people, this famous law that the taller people have shorter children and the opposite, so that generally the population height on average stays the same, but with certain variance being there. And that was the effect of regression. But any kind of relationship based on normal distribution and linear predictions, or later nonlinear, quickly became called regression. So that's why we are using linear models or nonlinear models, but nothing is regressing to anything. But that's the one of the charms of statistical nomenclature, that there are certain things happening there. And general understanding of regression models are models that provide you with numerical value that is explanation or estimation of a relationship between independent and dependent variables. When we take a number from, we try to estimate a number that can take a continuous values, we say about regression. When we take a number and or we want to generate predictions in discrete number of cases, usually we talk about classification. Not always, but usually. But generally, that's what regression is. So let us focus on an example. This is a very nice example that comes from the book by Richard McElrath. The book is here, Statistical Rethinking. It is a very famous data set from anthropology. This is a data set considering Kung people, who are one of the nomadic African tribes. When such tribe was being surveyed in the 60s, they've collected some data about that population. This was interesting because such model, such data consists of relatively isolated small population without any kind of civilizational pollution or some kind of changes coming from people of different backgrounds. We have similar backgrounds, similar biological profile, so this was very interesting data set for the purpose of data analytics. And we will now move to creating a model of such data set, which this data set actually is based on the representation of height of people in that population. So we had registered their age, their weight, their height, their gender. So this is a small data set, but of real actual data. This can be accessed from the GitHub of Richard McElrath. It's available. Just to make stuff relatively clear, my working environment is that I'm working on, as you can see, VS Code. I'm working with Command StandPy. I've installed the Docker that you are provided with in order to have a container. So I have a container here, which is for ARM-based Macs. Currently, I'm working on Mac Studio, so speed in compilation, especially, is rather significant. But that is just you know what's going on. I've accessed the container. Container works as my main source of computation. So that's just what you need to know. I'm using for my own visualization, I'm using my own package that is available somewhere in our repository. It gives you certain nice visualization tricks that are not any kind of groundbreaking, but can be useful, presenting the especially ribbon plots of quantiles of predictions. As I mentioned, I'm using command StanPy. I'm also using AVIS, the visualization package from for Bayesian computation, and I'm also using the standard stuff like NumPy, SciPy, Pandas, and certain visualization stuff from Matplotlib with a bit of styles from coming from Seaborns. I've selected my own colors here that are profiles defined by me. These are certain shades of blue. So just that you know what's happening here, I'm downloading the data directly from the GitHub and put it in the Pandas data frame. We focus on our data set at the moment, or for a simple analysis, we'll focus on the adult population of Kong people. So we'll get people over 18 years old. As you can see, the population is rather short. We've seen the heights coming on the level of 150 centimeters or so, with corresponding weights, ages, and genders. So having such data set, we can consider some kind of models. And sometimes we just need a baseline. And a baseline is a simple model that we can work on as some kind of predictive representation. And for the simplest way, we want to try to fit normal model, assuming that generally the height of people in this population is random. There is not dependent on anything. There's just a random distribution. It's a normal distribution, which, as we mentioned last time, makes kind of sense because growth is something that follows a normal distribution because it's a sum of controlled bursts of growth. So basing it on the central limit theorem, the sum of independent variables results you in the normal distribution. So we focus on a linear model without any predictors. We just assume that there is a constant representation, mean is constant for all the measurements. And for this point, we will use first try to consider a model, and we try to consider certain prior predictive checks. So we will take a model and we will provide it with some prior distributions, and we will try to to create samples are they corresponding to the data in a reasonable way. So let us open the Stan model. Here it's being printed, but I think it will benefit from color. As you can see here, our model works like this. It's this is a fitting model, not prior predicted model. Okay, this is just a generated quantities block for which we assume certain prior for me and certain prior for sigma. So the standard deviation. And how did we got these parameters? Because they are rather specific, why they're representing the height. And they come from general realization how the height would work. The average height of person in the world is, when I was creating this model, was 178 centimeters. So this is a good average at start. However, of course, we have taller and shorter people. So let's add additional variance in it. So we can relatively reasonably assume that 95% of people in the world will be between 138 and 218 centimeters of height. All people outside of those limits will be kind of extreme. Perhaps it will be more extreme on the higher end. There will be less occurrences of such situation because there's multiple multiple dwarfism elements that can happen to people, so that can be a bit more variance in the lower part. But either way, it's a good first shot. So that is the population. We assume that population on 95% is somewhere between 138 and 218 centimeters tall. Now let us assume what is the uncertainty. And uncertainty here is represented by the exponential distribution. I'm using exponential distribution because exponential distribution is rather nice with respect to I think that it can easily generate the height of it can generate values that are positive, so always nice for standard deviation, but also can easily generate both very small standard deviations also, but does not forbid you in reaching larger values because it's relatively heavy-tailed distribution. Not extremely heavy-tailed, but it allows you some bigger values. Not something that can happen if you, for example, select a half normal distribution for sigma. And so in our generated quantities, we just sample me from our normal distribution representing the actual height phenomena, population assuming it's normal, and we sample sigma, and from that we sample height. So we have certain measured height that comes from the population, measured with me, and with uncertainty of 1.5 on average of 1.5 centimeters, because so uncertainty of up to 15 centimeters. So we have a very broad option, an average uncertainty of 15 centimeters. So we were not measuring the heights very precisely, we just got them as there is. So what now? We can use this model to sample values. From the 15 centimeters comes from the fact that mean of exponential distribution is 1 over the parameter. So we get that model. We can simulate it. We compile the model, and we will generate 1,000 of samples. Newer version of command stanpy have problems with assigning zero warm-ups samples even for models consisting only of random number generators, because if you remember from your laboratory exercises, Stan models that in generated quantities only calls random number generators. It does not uses Monte Carlo there. So we are generating 1,000 of samples in one chain with fixed parameters, so it does not invoke Monte Carlo. With a given seed, we provide certain computation. And from that computation, we get, of course, in case of this 1,000, we get 1,000 samples of me, 1,000 samples of sigma, and corresponding 1,000 samples of height. And that can be, of course, visualized, as we can see here. The average is somewhere between 100 and 250 centimeters, which is reasonable. The uncertainty is perhaps big because we assume that it's possible to miss height of someone by 60 centimeters, but most of it is less than 20. So this is the most of the probability here. So when we simulate height like that, we get from 50 to up to 250 centimeters. It does not overshoot this 272 centimeters, so the world record for height registered in the history. So it's okay. These prior values are at least reasonable. We stay in the reasonable scope. So having observing that, we can start to move to how to get actual values of parameters, assuming that we have our simple model. And of course, we can take a new Stan model, and as I mentioned, it's easier to see with colors. So if we get our model, standard model of heating, we get a model that has in its data block, it includes number of samples and our number of or measurements, the number of measurements and the actual measurements provided as an array. We get set our parameters, we assign our priors to parameters, we assign our normal likelihood, and for the evaluation, we will generate new data based on the observed data. So we are generating here the posterior predictive distribution, or or it's going called by Michael Betancourt posterior retrodictive distribution. So we are predicting past measurements based on those measurements. Here is something that we will not be talking at the moment. This is a logarithm of likelihood, and for each of the individual measurements, but that will become clear what's going on here in a moment. So hopefully it will become clear. So we have our model, and we can fit that model using command StampI. We compile the model, we provide it with the data that we have here, and we sample it. So it was a very quick sampling process without any issues, and from our fitting of our model, we got that the mean that we've estimated is 154 centimeters, and it is rather concentrated up to 95%. As you can see, 94% of the estimated mean is between 154 and 155.5 centimeters. And we assume that our error of measurements is somewhere between 7 and 8 centimeters. We can then observe how actual our samples come from our model, and we can see that they are cover this kind of space. So for each of values of mean, we get a symbol which corresponds to this kind of contour plot. So it's almost normal looking. It's like an ellipsoid. There is the mode of the distribution, and this is the entire distribution between me and sigma. We can compare our model with actual data, and we can see that unfortunately why on average it's not horrible, because we cover the entire space. There are significant differences between predicted height and the actually observed ones. The black one is what we would expect, and here, as you can see, there are two significant modes, and our predicted height does not have that mode. This is, of course, a marginal distribution of height without any parameters. So what we can do? We can add some kind of predictors to improve our estimation process. The easiest predictor from our dataset that we can have, we don't have that much data, we have gender, we have age, and we have weight, and it is kind of reasonable that the taller people are heavier than shorter people, at least on average, because just there is more human there to weigh. And for certain improvement in analysis of this model, or interpretability of this model, we will want to center the weights of people. And why we want to do that? We want to do that because that will make understanding parameters much, much easier. When you center parameters, that is, or the outputs, you assume that 0 is something that corresponds to the mean of that value. So if you center the weights of the predictors, we assume that centered weight of 0 corresponds that this is a person of average weight. And then our two parameter models, alpha and beta, represents the situation this way, that maybe let's move to APPC. Alpha in this case, it corresponds to the weight of a person of average, or the height of person with average weight. Any change in weight will be represented by beta, by the beta parameter that will give us that our model will be change of weight with appropriate multiplied by beta plus alpha. So after centralization, we can create our model. So I guess again sample it easily from random number generator to generate 50 samples per each, and we can assume the virtual predictor as just a linearly distributed between minimal and maximal observed centered weight. So our model, when we sample it, provides us unfortunately to something that does not necessarily make sense, because our model proposes us relationship between weight and height corresponding to situation when there is possible for a person that weighs 30 kilos to be minus 200 centimeters tall. That means that they are 2 meters underground. That doesn't make sense. This is one of the simplest examples why using prior predictive distribution is a good idea. It is a good idea because it allows you to remove the nonsense values and stay somewhere that makes kind of sense. So we see that using this prior of normal distribution with standard deviation of 10 gives us too much flexibility and generates a model that are not physical. The same like this model allows you to have someone that is 6 meters tall at 30 kilos. So let's modify the prior. And what kind of modification is reasonable? Well, one of the ideas is, well, the height of a person usually will not be negatively correlated with their weight. People that are heavier are very often taller than shorter, just because there's more human, more mass here. So if a person is getting heavier, it's often correlated to the height, except in extremes, because with overweight people are also not very tall, not much taller than the situation. But in case of a healthy human, generally, as with observed with BMI and stuff like that, the higher person, to keep the healthy BMI has to be heavier. So we need to ensure that the relationship between the weight and the height will be positive. One option of doing that is using log normal distribution as a prior for beta. In this case, log normal distribution is a normal distribution that is distributed on the logarithms of certain values. So if logarithm of something is normally distributed, that means that the relationship, for example, in this case 0, 1, means that coefficient will be either equal 1 or 1/10 or 1 or 10 times. It will be a symmetric distribution in the logarithm. So how it will look like when sampled? Well, it will look much better because it generates mostly reasonable values that very rarely avoid the physical possibility of certain heights. So this model makes much more sense thanks to relationship to the only positive slopes. So if we take such model, we can consider what kind of predictions we can have from that. And using prior predictive distribution, we can sample outputs from it. And in this observation, we get something that is a bit too high in concept of a mean, but generally shape is kind of preserved. It makes a reasonable values. All the observed values, all those gray points, are possible under that distribution, or almost possible. So changing the height mean will not make much sense to do. So using this knowledge of prior predicted distribution, we can then create our posterior models, which we'll be using for fitting. So we provide it with data, including weights and heights. We can provide these parameters alpha and beta, and we can use transformed parameters to more conveniently compute mu, which will be then used in our model. In case of heights, we can get mu directly from vector matrix multiplication. In case of predictive generated quantities, we just use for loop. Either way is good. This one is faster. This one is generated quantities, so we use only this once after the entire sampling is complete. So it really does not much matter what's happening here. So if we fit that model, we get some kind of we can compile it, we can assign reasonable data, and then we can start sampling. And sampling from the distribution, we have 4 chains of length of 2000 samples. We get again a similar alpha, however we get a dependence of height, and we can see that using the unnormalized but centered distribution, it means that each kilogram over the mean of the weight of the population is suggesting the increase of height by 9 millimeters, or 1 centimeters plus minus 7 or more millimeter, hundreds of millimeter. So generally, beta will suggest that their increase is caused by between 77 0.77 centimeters to 1.02 centimeters. This is the estimated influence, and as you can see, the variance of measurements, the sigma, has shrinked. Before it was larger for the previous model, as you can see, not here but somewhere. Oh, here. Our sigma was between 7 and 8 centimeters. Here is between. Here it is between. Give me a second. 5 and 6 centimeters. So we can observe now how looks the mean of this entire operation. What is the estimated causal relationship between heights and weights, by drawing line for each beta and alpha pair that was sampled from our distribution. And the more we have them, the lesser the uncertainty here, and we get this ribbon plot that is quite nicely concentrated on the mean value here, and gets but these are of course the understanding of potential phenomena. When we introduce the prediction uncertainty, then we get something that is much more varying, but also covers most of the observed parameters, but not, of course, all of them. As you can see, our parameters are shrinking corresponding to the original priors, and we can see that beta is rather well concentrated between 0.7 and 1.1, and alpha is very strongly concentrated around this 154 centimeters. And this model can, for example, be used for estimating what is the distribution of a person of given weight of 50 kilograms. So then we can see how it's spread according to this model. But this is, of course, a simple situation when we consider the model of adult population, which on average should be similar to each other. However, if we add children, then this situation becomes much more complicated. So let us consider a complete data set here. And because we are now moving in much wider scope of possible values, we need to not only center the data but also standardize them, because we want to have our data, especially our weight, to be in reasonable scopes. And that comes because we want to introduce some kind of powers of predictors. And introducing powers of predictors with predictors that are large numbers, it's a problem that is asking to happen. So, having that, we can say that we can do standardized numbers. What does it mean, standardized? It means that it moves generally to a much more reasonable scale, and this scale says that instead of consider change by 1 is considered a change by 1 standard deviation. So such parameters are much more reasonable in this analysis. Okay. So we can then take our our expanded data set, and we can use it in order to fit our model of our linear model. As you can see, the change of mean is significant, but because it's much lower. But now, beta says the change of weight by 1 kilogram follows by increase of the height by 25 centimeters. This is something that is not really reasonable. But still, it gets some kind of model following. This is the part that we had previously, and these are the children and underweight people that are showing that there is some kind of relationship here that is not well captured by linear representation. And what is the method of what we can do in order to improve such situation? Well, we can add higher powers of our predictors. We can construct a much more significant expansion in the Taylor series. It's not necessarily always a good idea, but sometimes it can be nice because it can provide us with some kind of more flexibility. Also, it always results to the Taylor series, which says that our function can be represented as a function that is a sum of consecutive powers of distance from the point where the sample was represented. So this is again the standardized value starting from the mean, and moving from that standardization, moving by 1 is just a change of 1 standard deviation. As we can see here, as you can see, the weight here comes from -2 to +2 standard deviations, so that's generally 95%. So we can create our new model for prior predictive simulation, and this model is very similar. It just added one additional parameter and simulated the introduction of higher power into the situation. So doing that, we get a model that is not perfect, but it's not horrible either. Perhaps here it's even more significant than the 178 centimeters of average might be a bit too much. But still it's not horrible. The model will be able to contract, which is also important. So setting our model here, we get the summaries from the priors, how they are being generated, and of course it is rather consistent with what we observed before. As you can see, beta 2 is now between has a mean of 0, 2, and both possible positive and negative increases. So it's all over the world, less in prior. If we move to actual fitting, well, then the model is again very similar. We just added the additional changes in the transform parameters. We added additional prior, and this is the same situation as before. So this is the big advantage of working with Stan and similar languages, that you can really handle all kind of models without much hassle. And then of course we can perform some kind of fitting, and we can see that this model looks very nice regarding fitting our model. Maybe not perfect, but it shows us that there's a significant improvement if representing between weight and height. So this is all fine and dandy, but what we see here is some observation based on the data that we've used it to teach it, to perform the learning process, to fit the model. And this is of course a big no-no in the machine learning community, because usually you want to split your dataset into the training dataset and testing dataset. However, in this case, we have a very small dataset of 160, 170 people, splitting into the training and testing models would just remove information that would allow better learning of parameters. So what can we do in order to get the behavior of our model outside of the sample? How to check if this model should generalize or not? And for this purpose, we generally need to look at stuff that is being related to so-called information criteria. And those are used for model comparison. So let's get a bit of theory. We are actually working on the scientific paper by Professor Aki Vehtari and Professor Andrew Gelman and Jonah Gabri. Aki Vehtari comes from Finland, works in the University of Aalto, and he has a lot of success in numerical methods of different kinds for probabilistic machine learning. Andrew Gelman is important theorist regarding Bayesian statistics. He is one of the brains between the mathematics that constructed Stan and algorithm being done. Jonah Gabri is one of the people who wrote Stan and those stuff like that. This is a paper that's publicly available on Archive. Archive, which is written like this here, is focuses on methods using leave one out cross validation, a widely applicable information criterion, or otherwise known as Watanabe-Akaike information criterions. There are methods that can be used to estimate how the model will behave outside of the sample in a certain very specific way. Because those methods are focusing on estimating something that is called expected log pointwise predictive density. So this is how the probability of logarithm of measurements will behave when those measurements come from real probability distribution, and our information comes from the observed data y. And the general idea is to this value, the higher it is, the better it is. Or depending on the sign, it can be more negative. It is, the better it is. Generally, the main idea is that we can kind of get the information of which model is better or which model is worse. And the idea comes from the log pointwise predictive density. That was the value that we've seen before in our code, which we've computed for each of our models here. Oh, sorry, not this window. We computed the logarithm of normal likelihood, which is actually a function already implemented in Stan at given points. So this is a vector of likelihoods for each of those points. This will be important because this will allow us to estimate what happens when we do not have those samples. And okay, now the question is, does it switch to appropriate window or not? When I click it, it does not change. That's a bit of the problem here. And if I will close that, it just closed the window. Okay, so I will have to change the... I was too cute for the possibilities I wanted, but not worry. Save the changes. It just doesn't work for the multiple cards of the preview. Okay, so I understand that not the changes of the paper were not visible, as again I said, we are talking about this paper by Aki Vehtari, Andrew Gelman, and Jonah Gabry, and we are focusing on the estimating the expected log points-wise predictive density. So generally, the main idea for that is to compute this approximation. So here this is the sum of all possible new data points coming from the distribution of data points. So this is the expected value of this function. So logarithm of likelihood of new data knowing the previous data for each new data point. And this is very similar to the mechanism of leave one out cross validation, that is estimating a point. What is the probability of given point, knowing all the other ones. So the idea is that expected log predictive density can be estimated by logarithms of likelihoods of each of measurements in the posterior that is computed using all the remaining data points. And this is a known mechanism used in machine learning. You leave one point, perform computation, and test on that one point, and you do it for all points together. However, this can be computationally very expensive, especially during Monte Carlo computation, because if you compute using Monte Carlo computation, then you need to put all those Markov chains for each of those slightly augmented data sets. And that's, of course, not practical. The idea that is being used for that is that we can kind of avoid this problem using something called importance sampling. And importance sampling says that generally each of those points here can be computed using the likelihoods of individual points. So this is an estimator of the leave one out cross validation expected logarithmic predictive density. And this is a good idea with certain technicalities, because generally there is a risk that coefficients that are being estimated here are not might become unreliable, have too large values. That's the main contribution of Professor Vechtari and colleagues, is that they've introduced something called Pareto smooth importance sampling, because their idea is to introduce certain smoothing procedure to the importance weights to remove the problematic situation. Additionally, it provides you with certain diagnostic procedure allowing evaluation of data points in order to get something, to see how influential are they for the entire data set. And this method being computed is, of course, fortunately implemented in all the practical packages, like, for example, AVIS or other places. So as long as we provide, and all the computation is based on the logarithm of the density of each of those likelihoods. So all those things can be relatively easy computed when we want them. And additionally, we get this certain estimation of the parity distribution, which gives us certain information about what is problematic or not. The alternative procedure of estimating the expected log point density is the widely applicable information criterion, or otherwise known as Watanabe-Akaike information criterion. It comes from the classical result of Akaike information criterion, which compared the values of, which was computed by difference between fit of the model and the actual numbers of parameters in the model multiplied by 2. In case of WAIC, we used log point density that we compute on our points, and so the same quantity that we've used for CSLU, and we add the element of estimated number of effective parameters. And this is being computed using certain variance estimators from the same values of likelihood. And that gives us the values of Watanabe-Akaike information criterion. So let's move further into our problem. We will not be covering how the Y is computed, but generally it's an alternative solution to our problem, and we'll see how both of those works. And this is needed because while we saw that quadratic model was more efficient than the previous model, however, we had a problem of that we can have that problem if we get more models. It will be really hard to distinguish which one is better and which one is worse. So for this purpose, we've computed additionally model without predictors and models with not only quadratic function of predictors but also quartic and also cubic, quartic, and quintic parameters values. So as you can see, it can be powers up to 5 powers of weight, standardized weight, because if this wasn't standardized, those numbers would dominate everything. And we can now compare how those models look visually. So of course, a fixed parameter models does not capture this part at all, and nothing really gets well represented. What you can see here, those fluctuations in those in this plot, comes of course from the sampling artifacts. If we computed this, actually we could compute analytically, and there would be straight lines, because for each of those points there is the same uncertainty. If we use linear model, it's look like we've seen before. If it was quadratic, well, it's better. But if you use cubic, well, here there is an improvement, but maybe hard to tell. And now quartic and quintic are really undistinguishable from the cubic one. So which one we should choose? And for this purpose, we can use the above mentioned information criteria. And fortunately, we can use it very easily using AVIS, because we just compute the values as here. So, having that, we can see that the differences between predictors are there is a certain ranking which is the best and which is the worst. However, it's not that simple to choose just by that, because we can visualize those differences between models using this plot, which generally gives us an information of what the probabilities are of given point moving from one point to another, and we certainly see that those models differ from each other. Unfortunately, they differ by certain specific value, and this value is the estimate of ELPD. And this number doesn't have an interpretation. This number is just a number. If the higher it is, the better we are. However, is the difference by 100 significant or not? This is a very difficult question which we don't have much answers. And as we can see, quartic, quintic and cubic, as you can see, they are ordered. So quartic is supposedly better than both quintic, so higher order, and cubic, lower order. But the difference are very, very small. So as you can see, it's well after the comma, and again, those values do not have a direct interpretation. This is for estimated lib1 outcross validation, but the same results can be obtained using Wakai-Watanabe information criterion, with one problem that the code suggests that there are some issues when sampling from quartic, quintic and cubic models to estimate WIC. So as you can see, we have a tool for model comparison, which we'll be using in your projects later, and this is the option how to do this. As you've seen here, we've used the models by adding additional powers of predictors, just directly putting them into the code. And excuse me, I have children at home and they can be quite noisy. This is the way of adding predictors by just writing them into the code, and that can be sometimes rather unwieldy. So it's time more. Also, it requires from you to compute powers and powers of those functions in each sampling iteration. So it makes the sampling much, much slower. That's why the idea is that we can just provide pre-computed values of function of parameters, because model is still linear with respect to parameters themselves. So predictors can be functionalized outside, and this is called creation of something called a design matrix. For that purpose, we even have packages in Python and R that do it for us, but in our case, we just add using appropriate columns of our data frame, just adding second and third power here. And this, of course, can be very easily computed. We just have to change our model, that instead of giving predictors, we just add the number of predictors and appropriate design matrix. And as long as priors for beta parameters, which are now vectors, are the same, it's very easy to create such model by adding additional predictors with much ease, just by adding additional column to design matrix. And of course, this model compiles without much difficulty. It just needs a few seconds to do so. And after that, we can see how it samples. So the sampling is very, very quick, and we can observe how the predictions work, and they of course work exactly the same. But this is much more efficient computationally when to do than just adding additional predictors, and it's easier to change the model. Okay, I think that will be enough for today. What we'll cover next time, we'll move to the general nonlinear functions of predictors represented by using splines, and then we will move to nonlinear transformation of output variables. So things like logistic regression and stuff like that. Thank you very much for listening. Hopefully the lecture wasn't too boring. And we'll be in touch over summer, during next week and over summer, as we'll see. Thank you very much and have a nice weekend.